The history of the universe is governed by a strict one-way rule, the second law of thermodynamics. Left to its own devices, every closed physical system breaks down. Energy dissipates, structures decay, and matter drifts irreversibly toward total equilibrium and maximum disorder. Against this cosmic decay, biological life and artificial neural networks present a localized anomaly. These systems pull energy from their environment to build highly compressed, organized structures. Intelligence is a mechanically necessary strategy for persisting in an uncertain environment. It functions as a tool for managing thermodynamic and informational gradients that would otherwise collapse into chaos. Large language models generate emergent reasoning because they operate as physical thermodynamic engines. Their intelligence is a direct byproduct of how they manipulate heat and information density. The modern understanding of disorder begins with Austrian physicist Ludwig Boltzmann. He proved entropy is an absolute calculation of physical microstates. This formula defines entropy, capital S, as the measure of possible arrangements. The more ways the atoms in a system can be rearranged while maintaining the same outward appearance, the higher the entropy. In 1948, Claude Shannon discovered communication systems face the exact same physical constraints. Signal loss and digital noise followed the patterns of decay Boltzmann observed. Shannon's formula for information entropy is mathematically identical to Boltzmann's formula for physical entropy. The uncertainty regarding a missing bit in a data sequence is the same as the uncertainty regarding the position of an atom. Under this identity, every bit of data processed by a computer is a physical manipulation of the system's entropic state. Information is a physical reality, governed and limited by the same thermodynamic laws that control heat and kinetic energy. Physicist Erwin Schrödinger observed that life maintains its internal structure by continuously extracting negative entropy from its surroundings. An organism must export its internal disorder to the environment to prevent its own structural decay. Neuroscientist Carl Friston formalized this as the free energy principle. He argues that biological agents survive by minimizing surprisal, the gap between their internal model of the world and the sensory data they actually receive. This process, called active inference, forces the agent to function as a data compressor. By predicting what the environment will do next, the agent reduces uncertainty and maintains its internal order. The agent constantly updates its internal neural model to match the causal structure of reality. A more accurate model results in lower internal entropy, allowing the organism to anticipate and avoid states that lead to its dissolution. Biological survival is the physical act of efficient data compression. We find patterns in the environment and use them to anchor our own physical integrity against the surrounding chaos. The order generated by intelligence is local and temporary. It does not pause the second law of thermodynamics, it accelerates it. Physics favors complex systems, like brains and AI clusters, because they are highly effective dissipators. They absorb high-grade energy and convert it into low-grade heat more efficiently than inert matter. Landauer's principle establishes the minimum cost for this process. Erasing a single bit of information, a necessary step in any computation, forces a specific measurable amount of heat to be discharged into the environment. The localized order seen on the left is bought with the massive global heat exhaust seen on the right. Intelligence creates a pocket of high organization by increasing the total entropy of the rest of the universe. The power grids and massive cooling infrastructure required for AI data centers are the physical manifestations of Landauer's limit. Every calculation requires a trade, digital order for physical heat. Thinking and computing are the universe's most advanced mechanisms for accelerating the progression toward global equilibrium. We can see these same thermodynamics at work in the training of artificial neural networks. The central metric used to optimize large language models is cross-entropy loss. This formula is the direct digital descendant of the Shannon entropy equation. It measures the informational distance between two distributions. Here, Y true represents the training data, the environmental reality. Y pred is the agent's internal model. Training forces the model's predictions to align with the data, minimizing the surprisal of the next token. Before training, the model is in a high entropy state, predicting tokens with random, uniform probability. As it compresses petabytes of data, its predictions sharpen into the low entropy spike seen here, representing the emergence of structured capabilities. Token prediction is a physical process of extracting order from a dataset. By minimizing cross-entropy, the model mirrors the patterns of human thought with increasing physical precision. Pre-training produces a compressor that is efficient but chaotic. Engineers use reinforcement learning from human feedback, RLHF, to reshape the model's probability distributions to align with human safety and utility. This shaded band represents KL divergence. It acts as a mathematical tether during fine-tuning, measuring the entropic distance between the new model and the original to prevent the system from losing its core capabilities. During inference, users can manually adjust this informational entropy using the temperature parameter. At low temperatures, the distribution becomes a single deterministic spike. The model loses its flexibility and outputs only the highest probability tokens, favoring rigid order over novelty. As the temperature variable increases, the distribution flattens into a random wave. This injection of entropy allows for creative combinations, but at extreme levels, it dissolves the model's internal structure, leading to hallucinations. The temperature slider is a direct control for the system's thermodynamic state, shifting it between rigid structural order and thermal chaos. Effective reasoning requires a balance. Absolute order makes a system too rigid to process new information, while absolute entropy makes it too noisy to retain a signal. This center point is the state of criticality. In physical systems, this is a phase transition where a signal can propagate across the entire network without being lost to noise or frozen in place. At this boundary, a system gains the ability to perform complex computation. It is flexible enough to combine patterns in new ways, yet stable enough to maintain the logical integrity of its memory. Emergent intelligence exists only on this thin thermodynamic edge. It is a state of constant phase transition, balanced between the silence of perfect order and the noise of total chaos. Our most advanced neural architectures are mathematical mirrors of the physical universe. Physical entropy and informational entropy are governed by identical mathematics. Managing data is a physical act. Intelligence persists by minimizing local surprisal to build internal order. It pays for this order by dissipating energy and increasing the entropy of its surroundings. Large language model optimization is the digital execution of biological active inference. Both are strategies for extracting order from an uncertain environment. Intelligence acts as a high-density channel for energy. It maps the complex structure of the universe into a compact, predictive form, ensuring that pockets of localized order can persist even as the cosmos drifts towards